Hi everyone, welcome to today's lesson. We're going to be looking at quadratics, some of their properties, and some of the things we can do with them. Specifically in this section, we're going to be focusing on how to solve quadratic equations. And there's several ways to go about it. We're going to start with kind of the basics that may look a little more like, well, some of it looks a little more like our typical process that we go through in solving equations that we've learned to up to now. And then some of it takes a bit of a different turn. So that's how we're going to start out today. And so let's just look at some principles or some, definitions and ideas about quadratics. What are they? So we call an equation a quadratic equation if it's a polynomial that has a degree of 2. Remember that the degree of a polynomial is equal to the degree of its highest term, or the highest monomial within the polynomial. And so when we have a polynomial that is a second degree polynomial, we say that is a quadratic polynomial, or more specifically, a quadratic equation. We can get these from all kinds of situations. We've looked at mostly linear equations, but quadratic equations produce kind of a curved, almost U-shaped graph. And we see these arise in geometric situations, dealing with area. Also, when we're looking at the paths of objects in relation to gravity. So here's just kind of a start-off example that we could look at. Here we're talking about paving a square garden, and the cost is $3 a foot, and that's the linear cost. And then the filler dirt is $2 per square foot, so that's the cost per 1 by 1 square of the dirt we're going to put into this garden. So it's square, number one. And the linear cost for the outside parameters of that is $3 a foot for the pavement. And then we have the dirt that's going to go inside. So we want to create a cost equation for any, this would apply to any square garden that had these parameters. So if we had a square garden we were making, and the cost to make sort of the pavement along the outside is $3 a foot, and the filler dirt was $2 per square foot, this equation would represent the cost that you could expect. And so we're going to make x be defined as the length of one side of that garden. So if we wanted to picture this, and I always recommend you try to draw out any kind of story problem like this, and we're going to use x as defined as the length of one side. And since it's a square garden, really, you could see x would be the length of all sides because of the definition of what makes up a square, right? So we know that the cost per square foot, and x representing the square foot, is $3 per square foot, right? So per linear foot, sorry, $3 for each side, x being the length of the side. So 3 times 4x, since there's 4 sides, x plus x plus x plus x. This would be the total linear length, right? And x plus x plus x plus x, I think I said 4x's there, is 4x, or 4 times x. So we have that multiplied by 3. This would be the total linear distance, the perimeter of this garden. And then we're going to multiply that by the cost per linear foot, 3. All right, and to that, we would add $2 times the area per the square foot, right? In other words, if we divided this up, let's say it divided into 4 in either direction. This is just an example. It's not what x necessarily represents. But there would be 16 square feet, each of these being 1 by 1 square foot. So if we had 5, that would be 5 times 5, or just whatever my length is multiplied by itself, or squared, and then we're going to multiply the number of those squares by the cost per square, which is $2 per square foot. And so adding those up or simplifying them down, this would be the cost equation that we would have here. And notice that this is a quadratic equation because it has x squared there. Okay, and I also wanted to kind of demonstrate the other thing that we had talked about, which is the path of a object falling on the earth. And and my plan was to embed this video of this demonstration within this video, so a video within a video, but it will not link, even though I did link it in this document, it won't link. So I'm leaving it as a separate link for this video lesson. So you'll find this description there. So what I would do at this point is just kind of pause the video and watch that link. Okay, once you've watched that, we're actually going to create a function that models this specific example of the height of that ball. So this is a height function, h. So it's the height of my ball that was dropped as a function of time, where t is going to be in seconds. And so to do this, I know it's going to be quadratic. Let's just say we knew this ahead of time. This is the generalized form of a quadratic equation, where if there was, well, there would have to be a t, there would be a squared in there, because that makes it a quadratic equation. And we just happen to know that traveling objects in relation to gravity do function in terms of a squared. And then there's going to be some coefficient out here. So we just mark that coefficient with a b. And then a lot of times we'll also have a t variable in here. And so if there is, then we're going to have the coefficient of that t variable be b. And then a lot of times, probably most of the time, we also have a c, which is just a number by itself, not being multiplied by t. This is kind of this form here is actually the standard form of a quadratic equation. And the only thing that differs is whether, what the values of a, b, and c are. If there's no t term, for example, if there's no term involving t, b would equal 0, and 0 times t would just essentially get rid of this term. Or if there's no constant term, that c would be 0. The only thing that can't be 0 for us to actually have a quadratic equation is for a to be 0, right? Because once this is 0, now it's a linear equation, not a quadratic equation. All right. So there's a couple of points that if we want to model this equation, we need to figure out what are some 3 points of height in terms of time, right? Time and height, time and height, time and height. And so we're going to put time as our x. It's our independent, and it's causing or having an effect on the dependent variable, which is h of t here, which is our y. So our ordered points are going to be time and then the height of the ball. And looking this, there's a couple that stand out pretty obviously. The first is just the initial point where we started at time equal to 0. Before we drop the ball, it's being dropped from a height of 2.5 meters. And so 0, 2.5 is one of the points of this path. The other point would be at the end, right? When the height was 0, what amount of time had passed? And we saw from there that 0.7 seconds had passed before it hit the ground. So it had a height of 0. And then I just have to pick one more random point. Now, why do I have to pick 3? Quadratics with linear equations, we only had to have 2. Well, quadratics are a little more difficult in that we actually have 3 unknowns here that will define this equation, a, b, and c. And so we need a third point in order to establish this particular equation. So I just picked one of the random points from the path. Now I did simplify it a little. The actual value was 0.321, but I just wanted to keep this a little bit simpler. I just left it as at least two spots there. And the exact time was 0.2 seconds. Okay, and so we're ready here now to come up with the quadratic equation that models this situation. One of the things I want to make a correction here is this actually should be 2.32, not 0.32. It's 2.32 meters at 0.2 seconds, not 0.32 meters. So that number here is a typo. And you'll see it was the same typo on the previous page, so I'm just correcting this. Now, other thing I want to point out here is that you're not going to have to do this process. This is just more for you to watch, enjoy, and see how these things connect with each other. We're even going to use systems of equations as a way of figuring out my unknowns. Now, the unknowns are the A, the B, and the C. For any quadratic equation, these three are really the numbers we need to find. For any quadratic equation, it's going to have an A, one way or another. Otherwise, it wouldn't be quadratic. As soon as A is a 0, then the t squared becomes 0, and it becomes just bt plus c, which is a linear equation. But sometimes B might be a 0, and sometimes C might be a 0. So it's got to have this term, but then we have to figure out what the other values are for the situation. There would never be any other t terms, like terms involving t, because if there were, we would combine them into one term, right? So you can only have anything less than a t squared, so t, and then the other possibility is there's no t, so we just have a constant, a number by itself. But these three numbers are what we have to find. And we're going to use these 3 points to do that. All right, let's start out with the first point, which is a very special point to us. It is the y-intercept, where x is equal to 0. We know that this is a y-intercept. Without this being 0, this wouldn't be a y-intercept. And we generally will always use that because it's easy, if we can, in trying to find some unknown values. So we're going to start with h of O, which is a times 0 squared plus b times 0 plus c. And we know that the y outcome, right, the height at time equal to 0, we know what that is. It's 2.5. This becomes 0, because 0 squared is 0 times a is 0. This becomes 0, and then we're left with c. So we found one of them. We know c is 2.5. Generally, my c's tend to be the initial values at time equal to 0, or whatever the independent variable is representing. So now I can rewrite this general equation as h of t equals a t squared plus b t plus, I've got one of them, 2.5. So let's go ahead and put it in there. And now we use the next point, which is 0.7 and 0, which represents, after 0.7 seconds, the fact that my height was 0. Meaning that this was 0 when t was equal to 0.7. So that's a times 0.7 squared plus b times 0.7 plus 2.5. And subtracting 2.5 to the other side, we have now put this, what ends up being, this is 0.49a plus 0.7b. I just wrote them in a different order here because, and this became 0, so that they're in a typical standard linear form, which the linear form of an equation is ax plus by equal to c, where x and y are on the same side, so the two variables are on the same side, constant on the other. The other form we have is sometimes that we use the slope-intercept, y equals mx plus b, where we get everything onto the other side of the equation, with y isolated over here, because this tells me the slope and this tells me the y-intercept. But this also is another form. We call it the standard form of a linear equation. And the two are just rewrites of each other. And so now this is in a standard form. And I know that's a little confusing with the a's and the b's and the x's and the y's, but here we're just using or thinking of a and b as my variables, the unknowns, right? And the unknowns are what we're trying to find. That's one point. Let's look at the other point, which is 2.32, height of 2.32 meters, when time is 0.7. Or, sorry, is 0.2. So 0.2 squared plus b times 0.2 plus 2.5. And if I subtract 2.5 to the other side, we get negative 0.18 equals 0.04a plus 0.2b, which is another linear equation with a and b on one side, so we put it into standard form. Those represent my two unknowns. Okay, now to simplify things, let's put these into, let's write these so that they're a little easier for us to deal with. In other words, that they don't have decimals. And for this first equation, for me to get rid of all the decimal values, now you don't have to do this, but it does make it easier for us to think in terms of, and it doesn't change the equation, it just changes the way it looks. But it's a little easier for us to do with whole numbers. I think you'd probably agree with that. So to make these all whole, I would have to move this one 2 spots, right? Because it's got 2 decimals. So I'm going to multiply this equation by 100, meaning each term gets multiplied by 100, which moves the decimals 2 spots with the 2 zeros. And I'm going to rewrite it up here. So that would give me negative 250 equaling 49a plus 70b. And for the other one, it's the same problem. To make this whole, it would be 2 spots, and 1 spot. So we want to get them, all those coefficients to be whole, so I'm also going to multiply this by 100. Again, this is just to simplify the look of it for us, for our own benefit. So that gives me negative 18 equal to 4a plus 20b. Notice with the 4, it was a 0.04, 2 spots, put it here. And then with 0.2, we have to move it 1 and then another, so that makes it a 20. Here's where we're going to use the elimination process to find the values of a and b. Now I'm using elimination for the main reason that all the coefficients that I have are none of them are 1, right? And so to get any of them equal to 1, I would have to do some division, and then I've got fractions, and then it just becomes more of a mess. So elimination is the more logical of these two. So I just have to figure out which of the two I want to eliminate, whether I want to eliminate A or if I want to eliminate B. You always want to go for the one that's less complicated in terms of elimination. And in this case, 70 and 20, I can get this 20 to be a 70 a lot easier than I can get this 4 to become a 49. If I multiply 20 by 3.5, and actually I want to multiply it by negative because I want this to become negative 70, so that when I add these two together, my b eliminates and becomes 0. So I'm going to rewrite this equation by multiplying this one more time by negative 3.5. Again, that has to go to every single term as I multiply. And so that gives me, and since it's negative times negative, positive 63, and negative 3.5 times 4a is negative 14a, and then negative 3.5 times 20 is minus 70b. So I'm going to rewrite this down here as well. Now what I have is negative 250 equal to, 49a plus 70b. I just rewrote it next to it so that I can add these together and get my results. Here, as I wanted to be eliminated, and 49 minus 14 is 35, so I have positive 35a, and negative 187 here. And dividing both sides by 35, I get a is equal to negative 5.34. Now, of course, I did have to round this. That's obviously not an exact decimal, and I rounded it to 2 decimals, which is probably sufficient enough. But look what I found. I found another thing here. I found negative 5.34, which is my A value now. So now we can press on and find B, which is the last one. And the last ones usually go the fastest, simply because we found almost all the other variables, save for one. Okay, so because I found A, and A was equal to, now let me go ahead and write these up here again. There we go. These are the points I found. I want to find one more. So I'm going to go back to one of the original equations when I had gotten rid of the decimals and plug in what I have for A and B now. So it was, so if I plug in the value of A I just found, so I have negative 18, 4 times negative 5.34 plus 20b, I can now find the b. Notice I didn't go back to my original quadratic because at this point I'm just trying to find a and b. A is which I found, so I'm going back to the two equations that I was basically eliminating, right? And I could have gone back to the one that has the decimal, the 0.04 and the 0.2 and the etc., the negative 0.18. Or I could have gone back to the other equation. Doesn't matter, we just have to pick one of the two, substitute our A value in there, and use this to find B. So that's negative 18, and if we multiply this times 4, we get 21.36 plus 20b, and now I just solved this, oops, that's negative, solve this for B by adding this to the other side, so plus 21.36, add to both sides, really is what I should say, and that gives me 16.8, no, hold on, let me rewrite that, that was incorrect there. Adding these two together, we actually get 3.36, or 3.34. And is that right? No, sorry, 3.36. I'm making some errors here. Sorry about that. And then we have equals 20b. And then we divide both sides by 20. I get b is equal to 0.168. So, with uncovering both A, B, and C, I now have the equation for the plight or the flight of this ball. For A, it was so negative 5.34 t squared plus 0.168 t plus 2.5. Now, any of the rounding here, I tend to take things out, to at least 2 decimal places, sometimes 3. It may seem a little random, but I try to avoid rounding as much as I can. Just depends how accurate I need it to be. We didn't need it to be. There's not a real big consequence to this equation, so we don't need it to be accurate out to several decimal places. But we have now found the quadratic equation that marks the path of that ball. All right, so let's actually look at how we can solve some quadratic equations. Those are really looking at the functions, the models of quadratic paths, where you have an x and a y. When it's just, the x and y is already determined, then when y is determined, we want to look at ways we can find x. And so that would involve solving a quadratic equation. There's a couple principles we're going to look at which become really important and are going to integrate some of the stuff you did in the previous section with factoring. But in solving quadratics, we're going to use two principles. One is the square root principle, and then we're going to look at the zero product principle. So let's go ahead and start with the square root principle. There's certain equations that we can solve using this. You can also pretty much solve every equation using this principle if you know how to go through this process called completing the square, but we're not going to do that. But we are going to look at some situations where it's actually easier for us simply to use the square root principle. And the square root principle is very simple. It says you can take the square root of an equation as long as you do it to both sides. It's kind of like, and that should be a D there. I'm going to put it in black and make that a D. There we go, sides. It's always great when you find typos in the middle of a lecture. But this is an imperfect world that we live in, folks, so that's not going to be something I panic and go remake everything about. So I think you guys can probably deal with that. So the idea is kind of like what we do when we solve equations. We can multiply the entire equation by something as long as we do it to both sides and every term that's on both sides. We can divide, we can subtract, we can add stuff to both sides of the equation, again, as long as we do it to both sides of the equation. And so we can use that principle here in solving quadratics. The key is first getting the squared term alone on both sides of the equation. Now, let's take a look at this one, and it's kind of set up for us in that way. Almost. We have 3x squared equals 27. And looking ahead, I can go, okay, well, my term that has the squared is isolated. And I probably want to think, is this as isolated as it could be? Knowing that once I do have it isolated, I can take that step of square rooting both sides of the equation. Now, the problem with me doing it here is that I have the square root of 3. If I did that, I would have a square root of 3. And square root of 3 is not rootable. And so that would leave me with a square root of 3 x equals square root of 27, which we could simplify a little bit. But regardless, then I would have to divide by a square root. It just starts to get a little more complicated. And so I can make this a lot easier on myself by going back and simply performing a function before I take the square root on both sides. And that is just to get rid of the 3. Right? If I get rid of that, 3 goes into 27, which I can also realize. You can kind of look ahead at what's coming up, and see that, 3 is going to go into 27, so I'm just going to go ahead and get rid of that now. And now that I've got this isolated, I'm going to take the square root of both sides. Now, we can do this as long as a couple of things are observed. Number one, x squared actually has 2 solutions. So whenever I take the square root of both sides, I want to take both, or think about both as both the positive and negative solution. So the actual solution here is x not just equal to 3, but equal to positive 3 and negative 3. 2 solutions. And because negative 3 squared is equal to 9 and positive 3 squared is equal to 9, there's actually two roots to that. And so I can do that. We've actually explored this a little bit earlier in some other sections. So 2 roots, I want to take note of that. And of course, with these, we also want to go back to our original equations and see if they end up being solutions for our original equations, which in this case they do. Okay, great. So we've found the solutions for that equation. Let's go on to another one. This one, again, is also somewhat set up for us. What I would probably choose to do, since the squared is by itself, is to divide both sides by 4 to get rid of that coefficient of 4. So I have x minus 2 squared, and then 12 divided by 4 is 3. And then, now that I have that taken care of, I can take the square root of both sides. So I have x minus 2, and remember, this is equal to not just the square root of 3, but the positive and negative square root of 3. Now, I left it as the square root of 3 because we know that square root of 3 is not a perfect square. Now, it does have a decimal equivalent, but that decimal is an irrational number that does not repeat itself and goes on for infinity. So leaving it as the square root of 3 is actually more exact than approximating it. So I'm going to leave it that way. And then we add 2 to both sides. And we have x equals 2 plus and minus the square root of 3. All right. And so that is actually my two solutions. If I wanted to find their decimal approximations, I would just go 2 plus the square root of 3 into my calculator and 2 minus the square root of 3 into my calculator and find those decimal approximations. But this is sufficient most of the time because it avoids giving approximate solutions, and they're approximate whenever you have to round them. If you're rounding them, they're no longer exact solutions, they're approximate solutions, which in many cases is all we need. Now, of course, that process only works for certain things. It works for situations where I can actually isolate the x as a single variable on one side of the equation and get all the numbers stuff to the other side. When we look at a situation like this, if you try to get the x by itself, it's never going to happen. You actually can't unless you go through some processes that we haven't really looked at yet. There are ways that we can do that. But in terms of just using the normal processes for solving linear equations, it doesn't necessarily work. Like I said, it does for more complicated stuff, but we're not going to get into that for right now. So, this is one of the reasons, and actually I need a 0 in here. To solve something, it's got to be equal to something. So both of these should be equal to 0. If they weren't equal to 0, you want to set them equal to 0. Let's just say, for example, for this equation here, maybe it was presented as x squared minus 12x equals negative 32. Then I would say, okay, well, first let's set our quadratic equation equal to 0 by adding 32 to the other side. And the reason why is because in order for us to solve these, the first thing we have to have is their being equal to 0. That's because we're going to use this property or this principle that pops up when it comes to 0. 0 is kind of a special thing when it comes to multiplications. As we've talked about previously, anything times 0 is equal to 0. In order to get a 0 result from a multiplication, at least one of the factors, the portions of that product, must be a 0. In other words, if a and b equals 0, if we're multiplying them and I get 0 as a result, then we know either a has to be 0, b has to be 0, or maybe both of them could be 0s. That's the only way I would get a 0 product. And this idea, or this not really idea, but that principle is going to allow us to solve these equations using factoring. Because factoring is simply a rewriting of something as a product, right? Currently, right now, what I have here is have it in the form of addition and subtraction. It's a statement of addition and subtraction, right? I have x squared, I'm subtracting this, and then I'm adding that. So it's in the form of a polynomial being with all these three monomials, so a trinomial would be with addition and subtraction occurring. can I rewrite this in terms of a product? And that's what we were doing in the last section here. We were writing these in terms of a product. And so we know that with a trinomial like this, generally we have x and x. And with the signs that I have, I know if I have a positive product, that I either have to have a minus, minus, or a plus, plus. And we can look at this and tell what it's going to be. It has to be a minus and a minus because it's a negative sum. That the inners and the outers give me that negative sum. So I know that I'm going to have a minus and a minus. And so now I just have to find two numbers that multiply to give me 32 and add up to give me 12. And the two numbers that fulfill that role are 8 and 4. 8 times 4 is 32, and 8 plus 4, or more specifically, negative 8 plus negative 4 is negative 12. So now I've taken this and re-expressed it, right? I re-expressed this in terms of a multiplication statement. I am multiplying this times that. In other words, it is now factored. This is a factored polynomial. It's been re-expressed as a product. And thinking of this in terms of A and B, if I think of this as A times B, I know that I can get 0 only if the first parenthesis comes out to be 0, or the second parenthesis comes out to be 0, or both of them come out to be 0. Now let's take a look at A. With x minus 8, we have to think, what number would I plug in for x to get 0? Well, we can just not think about it and go through the process, and we see that, oh, if I put 8 in there, I'm going to get 0. And so with 8 here and 8 here, 8 being plugged in for x, this would give me 0 times, this would be 0 times 8 minus 4 is 4. So 0 times 4 would give me 0 as a result. The other way that I could get 0 as the result of a product is for this parenthesis to be 0. So x, in other words, x minus 4 being 0. And solving this, we get x is equal to 4. So I have two solutions here, 8 and 4. 8 and 4 are the two numbers that will make this true. And so they are both solutions. We can go back to the original equations and see that. Let's just take one of them. I'm going to do both, but going back to the original equation here, if I have 8 squared, so x squared minus 12 times 8, and then I add 32, do I get 0? Well, this is 64, and 12 times 8, I believe, is 96. My times tables sometimes get a little rusty over time. But yeah, 96, or minus 96, and then add 32. 64 plus, or minus 96 plus 32 gives me 0. And so that produces a true statement, 0 equal to 0. So that's how factoring can help us solve these equations. Now, of course, the downside is we can only solve these type of equations, these like trinomial equations, when they are factorable. In other words, that their results are not, square roots or weird things like that. So there are some limitations to using this. We're going to look at one of the other ways that we can do this. But for a lot of trinomials, factoring is one way to solve these quadratic equations. Looking at the other one, this is a little more complicated one, right? I have the 10, so I have an a value there that's not just 1 like it was on the previous one where I just had 1x squared. As you guys know, these get a little harder to factor. But let's just go ahead and do the kind of the hunting, pecking, trying to figure this out. The factors of 10 are either going to be 1 times 10 or 2 times 5. Usually they're going to be ones that are the two numbers. So I'm going to go 2x, 5x. Looking at my signs, I've got a negative here. I'm sorry, I've got a negative. I've got a positive 6, and I have a positive here. So that tells me it has to be a positive and a positive sign here. If my last term, my C value there is negative, then I know it has to be plus and minus to get a negative. And so we would just put the plus or minus in there and figure out later on which one it should go into. And then I want to look at the values for 6. 6 is either 2 times 3 or 1 times 6. We're going to go with the numbers that are closer to each other. Again, I want my sum to be 11. And we can see that 10x plus 6x would give me 16x, not 11x. And I'm realizing right now that I believe I made a mistake when I wrote this out. This actually has to be a subtraction of 6 in order for this to work. None of these combinations are going to work. So I'm going to go back a little bit, and we're going to correct that mistake. I apologize. If I wasn't able to solve this by factoring, which I wouldn't have been able to do that equation, then we have to use other methods, which we're going to go into in the next section. There are ways to solve them. They're just not solvable by factoring. And this particular equation, the way it's written right now, isn't, unless that's a 0. Unless that's a subtraction of 6 rather than addition of 6. So let's just rewrite that, and we'll start over here. Same principles. And, yeah. Okay, I'm going to start over there. So let's start with the 5x. And I know it has to be positive with a minus. So that's actually a good time for us to look at the difference there. It has to be plus or minus plus. I don't know which of the two. If I end up getting the right middle term or the right sum, but with the wrong sign, then I just change the signs around. So let's put 2 and 3 in here first. This would give me 4x and negative 15x, which is a great illustration here. This would be minus 11x, but I want positive 11x. So I got the right number and with my inners and my outers, but the wrong sign in front of it. And so that clues me in terms of what I want to do. I'm just erasing those. Is I want to do keep the same combination of things here, but simply change my symbols. So we're going to make this a plus, and we're going to make this one a minus. That's negative 4x and positive 15x. That's 11x. Perfect. So I found my combination. And once I've done that, whoops, I'm a little crazy on my erasing there. So this is a 2, that's a 2, that's a 3. I see I've got my A and my B. So I'm going to look at what x would have to be for 5x minus 2 to be 0, and for 2x plus 3 to be 0. To solve this for x, when you have the A there, the number in front of x, there's a number there. It makes it a little harder to just look at it and figure out the solution. But we are going to see a pattern here. So I have 5x equals 2, and then we divide by 5. We see x is equal to 2/5, and that's positive 2/5. And then for the other one, if I subtract 3, I have 2x equals negative 3, and then divide by 2, we get x is equal to negative 3/2. So 2 solutions, 2/5 and negative 3/2. Just to sort of look at the pattern so you don't have to go through that process each time, notice that my answer 2/5 was the opposite symbol of what I have here. And so it was positive instead of negative, and it was always divided by whatever I had in front of x. Now the opposite symbol is pretty easy to see how that is always going to be the case, because to get it to the other side of the equation, I've got to do the opposite thing, right? So for a subtraction, I have to add it, and for a positive, I have to subtract it. So that's always going to make it, here was a positive, and my answer for that one was negative. It's always this sign, this number, opposite sign, divided by whatever is in front of x. So negative 3 over 2. And so that saves you a little trouble if you can remember that little trick there. So factoring is another way that we can solve quadratic equations. This is especially true when we have middle terms like this. I want to go back for a second to this page and show you how, well, I'm going to do it with this one here, that we could have also solved this one by factoring. I wouldn't necessarily go back here and do that, but with this one I can. Because 3x squared, if I set this equal to 0, minus 27 equal to 0, we see that these two terms have a common factor of 3. Again, we always had to set it equal to 0 to use the zero principal thing. So I can factor out a 3, so that leaves me x squared minus 9 equals 0. And x squared minus 9 is a special thing. It's a difference of two perfect squares, which always factors out to be x plus 3, x minus 3. And so now I have three things being multiplied. This times this times this. And my idea is, what could I plug in for x to actually yield 0? And we see that negative 3 here would give me 0 for that parenthesis. Positive 3 here would give me 0 for that parenthesis. And so positive and negative 3 are the solutions there. So in this particular case, I was also able to solve this either using factoring or using the square root principle.